vectors kind of varies in calc too. Some of you guys have taken them in physics or you've taken them in pre-calc. So we've all seen vectors before. What we're basically going to work on is this worksheet that I have over here. And I just put it in chat. And it's also in the meeting invitation for today. And we're basically going to see, you know, how much of this worksheet we can get done. So before I put you guys in a group, I figured I would start with a couple of problems from the worksheet just to get you started. And then after that, let you guys, you know, again, see how many you can get done. We'll see if anybody else shows up. If it's just the four of us today, we'll just do a group of 3. But today, I just want to spend working on some vector-related problems because that's the most interesting thing about vectors is how you can set up some of these situations to look at what's going on. So we're going to do number 4 from the worksheet. Like I said, we'll do a couple together. And just to kind of get the hang of how I like setting these up, you guys might have a different way of doing it. So we have our 12-degree slope. And here's our car or object. And we know that 650 pounds of force holds it in place. So that vector has a magnitude of 650 and points in this direction. Now we have a weight of this thing that points straight down. Let's do what we were doing before and use the other color. Okay, now where I was making my mistake is I was trying to use the ramp as part of the right triangle. Where we're going to get the right triangle is we can think of this 650 as a component of the weight. So the weight's got 2 vectors. One that points in the direction of motion, which is the 650 pounds, and one that points perpendicular, which would be this one here that we're not trying to find right now. There'll be other problems where you find this component, the force that actually holds it on the ramp. Now, where our right triangle comes in, if I spin this thing around, we've got the 650 pointing out like so. And then we've got W, and that 650 is actually a component of W. So there's W. That's the 650. There's our right triangle. Now, here's the other thing we have to figure out. We need to know these two, at least one of these 2 angles to finish this thing off. Well, this week you're going to have to use a little bit of geometry. So we know that this angle here is a 12-degree angle, which is, so if we were to, we know this angle here then is 78 degrees. Now, each of these angles are going to be one of these 2. We just have to figure out which is which. So it might be better to kind of complete our right triangle on here to see. And remember, my drawing is not to scale. So if some of these angles look bigger or smaller, that's really more of an issue with my drawing. But think about what we know about angles that you learned back in high school geometry. This 78-degree angle is the same as this one because we've got a transversal here, and sorry, these 2 are parallel lines. Right, sorry, I pointed to the wrong one, I think. We have a 78-degree angle right here. So we know that the angle between these two is 78, which makes this the 12-degree angle. Okay. Sorry if I'm making this more confusing. Let me know if you have questions. My writing's kind of small as well. Let's zoom in on this. If I can keep this stuff from coming up. There. Now we've got a right triangle problem. We want to solve for the magnitude of W. We can use either angle. And now we see, now it makes more sense. Sine of 12 degrees, this is what I had upside down, is opposite over hypotenuse. Now here, you'll see these double bar lines. What this means is the magnitude of W, because that's really what we're looking at. The direction is given here by the angles. So solving this for W, we get the magnitude of W equals 650 over sine of 12 degrees. This comes out to be roughly about 3126.3. And now because the 650 was in pounds, this will be in pounds. Sorry, I was making the triangle wrong at the beginning, trying to make it the ramp. The triangle comes from our vectors. Questions about this one? Okay, then let's do one other one. Let's do an airplane one. Let's do number 5. So this was 4. So let's do number 5. Then I'll cut you loose on some. All right. So number 5, again, very common vector problem. We got a pilot who's heading at a bearing of 200 degrees, measured from our standard position, so that positive x-axis, at an airspeed of 350, and a 30-mile-per-hour wind coming in from the east blows her off course. So that means it's coming in and going west. And it asks for finding the plane's ground speed. So what ground speed is it's basically the sum of the airspeed and the wind together gives the ground speed, because the pilot's instrument says they're going 200 degrees at an airspeed of 350 miles an hour. But if you're looking at it from the ground, you see the wind included in that. All right, so let's see how we can set this one up. So we can put in some vectors and make sense. You don't have to do this on a set of axes, but I think it makes it a little bit easier to kind of think about where those angles are. Okay, so there's our axes for this thing. Oops. And we know that let's do one for the plane first. It's at 200 degrees. That put us down in the 3rd quadrant. So here's the plane. 200-degree angle. And we know that it's going 300, that its magnitude is 350 miles per hour. Okay, then what we want to do is we want to break this vector into components. So the plane vector has 2 components. And here's what's nice about breaking this into components, as you saw in the lesson, the numbers are right here, 200 degrees, 350 miles per hour. So for the I component, or the horizontal component, it's 350 times the cosine of 200. What's really nice about all this stuff is it just comes from our right angle trig. The horizontal component, we'd be using cosine. The vertical components, we use sine. It's 350 sine of 200 degrees. So that's the plane vector broken into components. We do the exact same thing with the wind. So we're told that the wind is coming from the east. In other words, it's going west. So it's going west. It's 30 miles an hour, I believe. Yep. And basically, we could put an angle in here, but we don't need one. It's going to have an I component, but no J component. But let's say we did want to do it the exact same way. And to show you that it still works out, this would be, to be going west, would be a 180-degree angle. So we would have 30 times cosine of 180, comma 30 sine of 180. Well, sine of 180 degrees is 0, so this is gone. Cosine of 180 degrees is -1, so this is -30, which makes sense for this vector. It's got a -30 I component and a 0 J component. Ground speed is just the sum of these two. So to find the ground speed, we add these together. And so what we get, I'm just going to change this to a -30 in the next one because we know the cosine of 180 is -1. So we have 350 cosine of 200 degrees minus 30. And over here for the J component, because we're adding 0, adding vectors, you just add the like components. One of the really nice things about vectors is how powerful they are, but how easy they are to use once you get a little used to them. So this is our vector in component form. And let's go ahead and we're finding the plane's ground speed. Whenever you see the word speed, that's the magnitude. So we know that the vector G is made up of these two components. The ground speed is the magnitude of this vector. So we're going to find the magnitude of G. And the magnitude of a vector is the square root of the sum of the squares of its components. So 350 cosine of 200 degrees minus 30 squared plus 350 sine of 200 degrees squared. And now we can go and calculate what we have. Be sure when you're doing these that your calculator is in the right mode. You know, most of the stuff we've done so far this semester that's involved trig functions, it's been in radians. But this is something we can put in all at once. So we got the square root of 350 cosine of 200 minus 30 squared plus second term, we have the 350 sine of 200 degrees, and once again, squared. I put that too early. Still need to finish off that set of parentheses. All right. Let me start this again. All right. Okay, 350 sine of 200 degrees squared. Okay. And there is our ground speed. Notice, and this is where we want to make sure our answer makes sense. The wind that's blowing us is going west. Well, we were already headed in a bit of a southwest direction, so it should actually increase our overall speed, but it definitely shouldn't increase it by any more than 30. Since these are going in a very similar direction, there's only 20 degrees between them. We see that we're almost adding on the 30 degrees of the wind, but we're not getting the full component of the wind vector in the direction of the plane. We're only getting part of it because there is a piece that's perpendicular. The other thing that we sometimes do with these problems, so we've created a resulting vector by taking our 350, our plane, and adding on the wind. Now this creates a new vector that is G. So there's that vector G. We know that its magnitude is 378 miles per hour. What if we were asked to find the direction? So let's go ahead and find that too. Well, to find the direction, again, it's right angle trig. You know, if I drop in a perpendicular here, I've got basically right angle trig. I'm going to have a horizontal and a vertical component. And basically, we're going to do an arctan. Tangent relates opposite over adjacent. So basically, your J component over your I component. So we're going to do an inverse tangent of, now here's where I personally like to use positive numbers. And we'll account for the fact that it's in the third quadrant. We'll make sense of that here in just a second. But it'll be the 350 sine of 200 degrees over 350 sine of 200 degrees minus 30. And our answer should make sense. That's why we want to draw these pictures. Again, guys, if you have questions as I'm going through any of this, feel free to ask. Let's see, we got 350 sine of 200. That's going to be divided by 350 sine of 200 minus 30. Close the parentheses for our denominator, and then close the parentheses for our arctan. And there's our answer. Okay, no wonder. Now here's the thing. Notice I got 38.64 degrees. That would put me actually past the blue line. So we noticed right away that there's something wrong with this one, and it is because I put in sine for both of them instead of putting cosine in this one. Now we should get an answer that makes sense. Oh, I put those in backwards. I am having a day here, guys. I apologize. I put the sine and cosine in backwards. I'm not sure how I managed that. There we go. Now we're going to get an answer that makes sense. We should have gotten something less than 20 degrees. Now this is just the reference angle. So we get that our angle is about 18.45 degrees. And if we wanted to give that a direction, we might say south of west. Or if we wanted to measure it all the way from the beginning, we just need to add the 180 that gets us over to this negative side. So measured from a standard angle, we would have 198.45 degrees. I know this problem didn't ask that, but I think there's another one in this worksheet that does, and I wanted you to see it.